For decades, extracting minerals from passing space rocks belonged to the realm of science fiction. Today, it has become a high-stakes engineering reality. To see the primary obstacle, we look at a 2D physics visualization of a deep gravity well. Notice the massive energy output required just to push a tiny payload mass to the top. Launching basic construction materials and heavy rocket fuel off the surface of the Earth is punishingly expensive. When we look at the vast, empty distances between the top of that well, the Moon, and Mars, the problem compounds. Ambitions for permanent lunar bases and deep space missions are stalled by this lack of local, in-space materials. Humanity cannot build sustainable space infrastructure if we must drag every steel beam and gallon of water up from Earth. Securing local materials makes off-world resource extraction a strategic necessity. Traditional mining concepts share a major operational flaw. They rely on setting up complex, heavy industrial extraction equipment millions of miles away in deep space. The strategy now being developed abandons that model entirely. Rather than mining the asteroid on site, the objective is to capture the rock whole and bring it back. Bagging an asteroid relocates the raw materials to where they are most useful, changing the logistical focus from deep space distance to strategic orbital positioning. Long before any hardware leaves the launch pad, the mission begins with rigorous astronomical surveying. Astronomers scan for a near-Earth object, or NEO, an asteroid or comet whose orbit brings it close to our planet. An ideal target contains high concentrations of water or platinum group metals. Platinum group metals are rare, durable elements like platinum and palladium used in advanced electronics. This radar-style chart shows Earth's orbit intersecting with dozens of potential asteroid paths. Navigators must filter these down to find a precise, interceptable trajectory, because the orbital mechanics of reaching the rock are as vital as the asteroid's composition. The successful launch of a specialized mining craft relies on finding a mathematical convergence of valuable materials and an accessible orbital pathway. To begin the capture, the spacecraft must synchronize its rotation and velocity with the asteroid, matching the rock's specific tumble in the vacuum of space to remain stationary relative to the target. Then, the pivotal maneuver begins. The spacecraft deploys a massive reinforced capture mechanism to completely enclose the spinning asteroid. This solves a major engineering hurdle. If you press a heavy drill into a surface without gravity, the force just pushes the ship backward. Wrapping the asteroid eliminates the need to land and stabilize on the surface. The containment bag firmly secures the main body, while simultaneously trapping any loose debris that could damage the ship in microgravity. Once the asteroid is locked inside the containment system, the mission shifts from exploration to active industrial logistics. With the payload secured, the spacecraft activates high-efficiency solar electric propulsion to begin the towing process back toward Earth. This vector map illustrates the energy and precise physics required to alter the trajectory of a massive celestial body. Constant, low-thrust propulsion gradually bends the object's path. The goal is to tow the bagged asteroid into a stable parking location, specifically a controlled lunar orbit. Once parked, the spacecraft deploys automated solar concentrators and robotic extractors to begin processing the raw materials directly in orbit. These automated systems must execute complex refining tasks while surviving intense cosmic radiation and the absence of gravity. With the asteroid secured in a stable orbit and the extraction units active, a former navigation hazard is now a functional orbital resource depot. The successful relocation of the asteroid achieves something humanity has never had: a functioning, off-world industrial supply chain. This chemical breakdown shows harvested asteroid water electrically split into base elements, creating distinct hydrogen and oxygen pools. Recombining these creates high-grade rocket fuel directly in space. The asteroid becomes an orbital gas station. Local fuel production reduces the cost of deeper space missions, allowing future spacecraft to refuel in orbit and bypass Earth's gravity well entirely. While the engineering is feasible, establishing an off-world economy creates legal and economic tensions that current international frameworks were not built to handle. First is the fundamental legal conflict of ownership. Under current frameworks, there are fierce debates over who holds the rights to a relocated celestial body. Then there is the risk of a macroeconomic shockwave. Suddenly injecting massive quantities of previously rare platinum group metals into the global supply chain could destabilize terrestrial markets. The goal of an asteroid mining mission is not to enrich Earth, it is to harvest celestial commodities that establish humanity as a solar system-spanning economy.